subject matter timing. Okay, so let me share screen. So the class is now on Zoom. And I will try to get it on the projector as well. Okay. Right, so I call this the optimization theory quick start. So first of all, why am I doing this? I'm doing it because basically whether it's supervised learning or unsupervised learning or semi-supervised learning, at the end, to get a model, to get a classifier, you need to minimize a loss function in the case of machine learning. In general, I remember when I took a grad course at McGill, it was taught by a lady at the math department, and what she said at the beginning of the class, it stuck with me. She's like, well, you guys are engineers, and engineers like to do things optimally. And I guess that's true. Like in all of engineering, there's like there's this prevalence to come up with the best possible solution. So optimization theory is just a mathematical framework for doing that. And so I'm going to run through 3 examples here of minimizing functions. And we're going to start very basic. Okay, so we have the following. So all of these are going to be scalar functions. So remember, there's the argument, the input, the argument, the independent variable of a function, which can be a scalar or a vector. That's W. That's a scalar here. And then there's what the function returns, which can also be a scalar or a vector. And a scalar here, and it will be for all the 3 examples. We don't deal with the case of vector or matrix functions. So this gets, like, for example, you can have F being a matrix and W being a matrix, and then that becomes really difficult because then you have like you have very, very many partial derivatives in that case. But this is the simplest case. F is a scalar function of a scalar parameter W. So you can think of W as I'm using W to signify that this is what we do in when we come up with the best classifier. We're solving for the W that minimizes some function. Now here, this function is a very straightforward quadratic. So first of all, how did we, let me go to the next slide. So we want to find the value of W that minimizes F. And the way this is written, so I want to unpack the syntax so no one is confused. This means that W star is the value of W. So out of all possible W's, W star is the one that minimizes F. Okay, so before I ask you how we do this, do you guys remember how this was done in high school? Because in high school, you did this, although it wasn't posed this way, but for a quadratic, do you guys remember how they teach this in high school? If a quadratic and you want to sort of, yeah, no, intercept, it's related though.
Minus B over 2A.
What's that?
Minus B over 2A.
Yeah, exactly. Minus B. So what was that called? Do you remember what that was called?
The vertex.
The vertex. That's right. They taught you guys the vertex, right? So and they taught it as in like it was, you learned how to plot. You put in a W, you get an F. You put another W, you get an F. But then you connect it to parabola, and then you would identify the vertex as from the graph, and then they gave you a
minimum or maximum.
Yeah, that's related. Oh, actually, I think I've had this idea for like years, and I finally had the foresight to make it. I have some chocolates today, so I may ask a question or two that if you guys get it, I'll give you a chocolate. One of the benefits of this is that, and if you don't like York thins, I don't know why they made these thin. Was that? No, it wasn't that kind of a question. Come on, that's high school, bro. Why do they have to make these thin? Like the world's gone crazy. Nobody eats Yorkies if they're concerned about calories. You know, it's like, yeah, okay, now each of them is only.
That's not your chocolate to mint ratio.
Oh, yeah, I like the mint.
They're
I hear
minty?
you.
Yeah, baby, you're
Oh,
less
minty.
Oh, okay. I have to bring in other hazelnut or something.
I think that's up to the infant, so if you want more of the chocolate side of things, you're changing
Yeah.
that ratio.
I hear
Yeah,
you.
but who wants more? Like, if you're getting the York ones, you want it for the mint. No one's eating a little bit of it. I kind of like.
Okay, I have to bring in different. So number one, by doing this, I will not eat the whole bag. Number two, but I want the thing. These are now only 32.5 calories each. The thing is, you're just gonna eat more of them. This doesn't work. Like especially milk chocolate, like dark chocolate, you don't need a lot to feel full. Milk chocolate, I can eat it. We go to the M&M store with my younger daughter. Man, I devour those M&Ms. Not sure how I got on that. Oh yeah, okay. Here we go. So we want to find a W star that minimizes F, but let's not use the vertex. How do we do this formally? What do we do? What's the math? Like, how will we get that vertex without using the formula?
Second derivative, isn't it?
Second derivative, no.
First derivative.
First derivative,
Second
yeah.
derivative tells you if it's up or down.
Yeah, that's second derivative. Yeah, we'll get the second derivative, right? So this requires, so we need to solve, so this is the equation. This is what I was saying, I think Newton came up with, which is amazing. To minimize or maximize a function, depending on whether it's convex or concave. So this function, do you guys know whether this is convex or concave?
Depends on any, right?
Yeah, very good. Very good. All right. That deserves. You get the first chocolate. I don't care. Give it to the person that answers
Yes.
your question. No, he doesn't have to eat it in class, but if you do, that's awesome. That's good sportsmanship. So it depends on A, right? And so, and I'll draw a little picture on the board of what convex actually means, but convex also means that if you solve it, there's only one solution to this. So the W that minimizes this, there's no other W that satisfies that equation except for the minimum of the function, which is really useful, right? And so we need to differentiate F with respect to W. I wrote this as a partial derivative just out of habit, but we didn't need partial derivatives here because there is no other variable, but it's just commonplace, right? So the derivative of this function is 2a W plus B. Set that to 0 and solve, and you get negative B over 2a, right? Very satisfying when you see that what they taught you in high school, you know, actually, I think the way they teach it is they just tell you this is a vertex, right? They don't tell you why. And I feel like to some extent, universities taught that way too. Maybe too much so. But this is the actual reason, because F is a convex function, which means that it only has one local minimum, which is also a global minimum. And the value of that minimum is related to the coefficients of that quadratic. All right. So now I am actually going to switch back to MATLAB, and we're gonna do this. So I thought it would be good to actually, even though this is a simple problem, and you wouldn't need to solve this numerically, I think that is useful. And the MATLAB script that I'm using, I did post on Blackboard. So we're going to minimize this numerically in MATLAB, and we are going to compare it to the theoretical solution. All right. All right. So my folder here. All right. So I'm gonna set up, first thing I do is I'm gonna set up my I'm gonna set up my function. And so you probably, I'm not, maybe some of you have used this syntax. This is called a function handle in MATLAB. And what it basically whenever the MATLAB interpreter, whenever it sees the at, it means it knows that you are telling it that what's coming is a function. Like what I mean by function is like a computer programming function that's going to take W as its parameter, and it's going to evaluate that, and you can call it. There's a couple of different ways to call this. So, okay, so I evaluated the cell, and you see that fun is a function handle with this value. So I can do things like function of 10, and it tells me the number, function of -10, etc. And so what I can do is I can plot this, for example. I think I do this down below anyways, but I'll do it here. So now linspace is just a useful function for getting a grid of points, a one-dimensional grid of points. And I can plot my function. So I can plot my quadratic function here. And so A, B, and C, A, B, and C are chosen randomly. However, yes, I want A to be positive. Why? So otherwise it's going to be what? Yeah, right. Okay. Yeah, I'll give you a chocolate for that, even though Emil kind of already answered. But there's one more. Why here? Why is it though? So there's one other piece. I'm not expecting you, because I think maybe you were implying it, but why is it that I couldn't do why couldn't I treat it as a maximization problem? Why do you think,
Because it has two values.
No. Why is it that so like, okay, so what if in your experiments, what if in your problems you have a function that that you want to maximize it, you don't want to, like, what if it's like the objective function is something positive, like God, it escapes me. Oh, the expected profit or something. You have a model for stock market prediction, and your model is outputting your models are outputting the expected value of your predictions. You want to maximize that. So how do you do that in practice? Yes, very good. I feel like that deserves a chocolate. That's really good. Minimizing the negative. So, and if you, here you go. My wife is always throwing me stuff in the house, and I'm always doing that. So don't feel bad. The rats from next door will find the York thins. And so, yeah, so exactly. So what I'm getting at is these functions that we're going to use. We're going to use this function called fminunc, which stands for function minimization unconstrained. They're all formulated as minimizations, right? And so there is no fmaxunc. There's only fminunc, but that's okay, because if what you want to do is maximize, you just minimize the negative or the inverse or whatever, however you want.
What is the reason for that?
I think it's just convention. I don't know if there's any. I don't think there's any reason that, it's the same thing. Yeah, no, yeah, it is. Yeah, I think they just didn't want to have to code double, every function twice. I don't know. Okay, so how do MATLAB? So I'm going to show you just quickly, because fminunc is actually something that there's two functions in MATLAB that are like super useful. Fminunc and fmincon. Those two functions are used extensively. And so fminunc will basically, you define any function, and the only requirement is that it you can evaluate it with this function handle fun. And then you start the search. X0 is the second argument, and X0 is the starting point of your search. So it does a search. It does they have very sophisticated routines, but it's basically doing a form of gradient descent. But it doesn't actually require you to define the gradient. It can figure out the gradient numerically for you. But it's solving this problem. It finds the x, it minimizes f, and you specify f. So it's very generic, because f can be anything. And so what we're going to do is we are going to run fminunc on a really simple function. And we're going to start it off. We're just going to start off the search at 0. And we're going to see what we get. Okay, and what is it says is local minimum found. That's all it's ever going to say. It will never be able to tell you that it's got a global minimum because it will not know that. And it says optimization completed because the size of the gradient is less than the value of the optimality tolerance. So optimality tolerance is some very small number, positive, and it's something like 1 times 10 to the minus 6. And what this function does is it evaluates the gradient, and then it moves along the gradient. And then when it gets to a function point, when it gets to an x where the gradient is very, very small, it says, okay, this is the plateau, this is the bottom of the hill. I'm going to stop here, and this is the minimum of the function. So now let's see what W star is. Okay, so W star is negative 0.1848. And now let's see what the theoretical value is. The theoretical value is very close. So if we do the percent error, so it's a super, super small error, right? And then we can plot this, and then we can see that.
What would you do this instead of minimizing the function?
What's that? What's the question?
What would you do this instead of just like minimizing the function by itself? Do you have the data beforehand, or you just like?
Yeah, the data is the training set in this case.
So what then you just like find the minimum?
That's what we're doing.
Yeah, but
So fun, right? Fun we defined here with A, B, and C, but in our case, in the machine learning case, there's no A, B, and C, but there's X and Y's, and X and Y's are right. Okay, so step 1 is complete. We got the function. We actually what I should have done here is I should have plotted both the theoretical value on the curve as well as the empirical, right? So they're both the same. You only see one because they're on top of each other. So sure enough, this thing works. All right. So that's, that's the case of a 1D function. Now we're gonna make it a little bit more complicated. Now we have still a quadratic function. So we have f as a scalar, but w is a vector, right? So again, we're not dealing with vector functions, the function of a vector parameter. And so this is how we define a quadratic in multiple dimensions. Right. So the question now is how I need to find the vector w that minimizes f. So the formula looks the same, except that I'm using boldface font to signify. So the convention is that lowercase boldface is a vector, uppercase boldface is a matrix. Right, so A, for example, is the matrix A, it's a matrix. B is a vector, and C is just a scalar. So how do we find this W star? And the W star should be bolded here. I apologize. What do I do here? What's the word I'm looking for? I mean, last time we just said take the derivative of f with respect to W and set to 0. So here we're going to be doing something very similar. Right? Because the difference is now there's multiple W's. In the simplest case, there's 2 W's, right? So we need to find the gradient of f and set it to 0. So maybe I have to put this on the slide, but what I'll do is, so the gradient of f, so I think everyone's here, but oh, did I want to do that? I guess it's okay. Stop sharing for the sake of our massive YouTube audience. So I have I gotta remember to buy myself a mic that I just like one of these little mics. So audio doesn't carry well when I'm here. So the gradient of function f with respect to W. So let's take the case where W is just 2-dimensional. So W is, there's W1 and W2. And so what the gradient is it's a column vector usually, although I suppose you could define it as a row vector as well, right? So it's a 2-element vector where the first element is the derivative of f with respect to the first element of W, and the second element is the derivative of f with respect to W2. Now, we do not need to, all right, and our function is this. Right, so one way to do this, the cumbersome way, but the way that always works, is I can expand this into, I can say this, I'm going to define my function in terms of scalars. I'll write this and I'll get out of the way so you guys here can turn around. What you're going to see is that this becomes very annoying because now I have, that first term there on the right hand side. It's gonna look ugly because you're gonna have 4 or 8 terms. I guess 4 terms, but it's just going to get cumbersome. And you could write out f, right? So I guess I'll continue for a little just to make sure you guys know what I'm trying to say here. I could say this term is going to be, and then this is going to be, be, this is a comma here. Okay, so that's written in terms of scalars. And there's no more vectors here, right? And so what I could do is just take the derivative of this with respect to W1, plug it in there, take the derivative of this with respect to W2 and plug it in there. And I have two equations, two unknowns. I set it to 0, I solve. Or two equations and set them both to 0. Yeah, two equations, two unknowns. But I don't want to do that. That's super annoying, especially when you get the complicated function. So I want to do I want to use symbolic gradients. So this you probably, this is what's really sad is that sorry, I'm repeating myself, but they teach you guys all this calculus, but they don't teach you, I don't think, any linear algebra, which is really sad. Because the linear algebra in the world that the workforce that you're entering is really important, or it's really good to know. It's good, it helps you navigate all the common modern tools for data science. Okay, so, right. So this is, I'm just gonna, because I want to get to the Lagrangian. So this is the expression for the gradient of this function. And so how did I get it? Well, I think it's easy to see that the gradient of this term is just b, right? Because it's just like the gradient of the derivative of a times x is just a, for example, right? So the b is just linearly multiplying w. So the gradient of b transpose w is just b. So this is the, I guess what I'll do here is I'll try to give you the analogy to scalar. So if you have, if f of w was w squared, aw squared, then the derivative of f with respect to w, just using the power rule, is 2aw. And so now if w is a vector, which I'll denote like this, and then you have, then the gradient of this quadratic with respect to w is 2aw. So this is a matrix, this is a vector, right? So the product of a matrix and a vector is a vector, and the gradient is a vector. And so that's what this term is. This is like the power rule applied to vectors, right? And then you can solve this function. So now remember, this is a vector function. You're looking for the vector w such that this becomes 0. And if you rearrange, you get -1/2 the inverse of a times b. Now, one thing about this is a needs to have an inverse for the solution to exist, right? So I guess one thing to think about is, oh, right, yeah. So what is that? How can a quadratic, so what I was going to ask is, how can a quadratic not have a minimum or a maximum, right? Because and actually what it is it's, I'll answer your question because it's kind of a trick question. Not every a is valid in this equation. A has to have a special, for this to be a quadratic function, A has to have a special property. It has to have a property called positive definite. It has to be, it's called it has to basically, the way to think about it, has to be a symmetric matrix. So in two dimensions, like what the A here, basically the diagonals can be whatever you want, but the off diagonal terms have to be equal to each other. So these two have to be the same number. That's the way you should think about it. And if it's not, then you will not be able to this will essentially not be a quadratic function, is I think the best way of putting it. All right, so we're gonna go. Oh yeah, sorry. Thank you. Yeah, it should be A21, absolutely. Thanks for catching that. Okay, I need to what do I need to do? If I go to, well, my MATLAB's not even showing up. Close it. There's some weird interaction between PowerPoint and MATLAB that has like MATLAB will close spontaneously when a PowerPoint's in full screen on a Mac. All right. This is not right. So here's, I'm going to set up my 2D unconstrained minimization problem. So I'm going to make my dimensionality 2. This is going to be my A matrix. I'm going to make my B and my C random. And here's my function. All right. So let's, so first of all, let's evaluate this. And so, for example, I can evaluate this for arbitrary, for like 1, 1, for example, right? Or, whoa, that was weird. For 0, 0, it should just be equal to C, and then etc. So now fun takes a vector W. So let's run fminunc again on this function and see what we get. Okay, it converge pretty quick. And this is the answer that I got from the minimized fminunc. And now let's see what my closed form, my theoretical solution is. And you see it's pretty much the same number, a little bit off. So great. So now we know how to minimize a two-dimensional function in MATLAB or on paper. But now we get to the interesting case, and this is the case that we encounter. Okay. Right, so now we talk about constraints. And so in the previous problems, I was free to choose any W that I wanted, which makes it easy to solve, or easier, but it's not in most problems, you have some constraints on the solutions that you can pick. So for example, machine learning, anytime you apply a regularizer, you add a constraint. So this is, I think, a really nice example to work with when explaining constraint minimization. I have a quadratic subject to a linear constraint. And so I will try to draw this on the board first so that to give you guys an intuition. To give you guys an intuition of of what I'm trying to do here. I have a quadratic with a linear constraint. So I'm gonna again assume that I have two dimensions, W1 and W2, and my function is that quadratic. I want to minimize it, subject to a linear constraint, which is d transpose W is equal to 1. In other words, d is given to me, so d is a part of the problem. So I have to pick a W that basically satisfies this equation, which means that it project. I can only pick W's that project onto D with a length 1. And so that my quadratic, any quadratic has elliptical contours. And the constraint here, which I'm going to draw in green, just depending on what D is, I'm just going to say the constraint is like that. And so I need to pick a value on this green line. I'm talking about just giving the geometric interpretation of this problem. I need to pick a value on this green line at which that elliptical function is minimum. So where is that point? Where is the minimum in with the contour and the line that I've drawn? Where's the minimum going to be? Where's my W star going to be in the plane? Closest to the center.
Well, not closest to the center, but like to the contour.
Yeah.
I don't know. It's fine.
Yeah, I know. I think it's something like it's interesting, right? So it's going to be, but so, in most cases, we're not able to visualize anything above 2 dimensions, maybe 3. And so, and that constraint is a problem because now I can't just take the derivative of my quadratic and set it to 0 because I have the constraint. And so I think this was 1700s, maybe in 1800s, so Lagrange came up with this idea of using Lagrange. It's called the technique of Lagrange multipliers. And so to understand the technique, let's look at what the Lagrangian is. So the Lagrangian is it's a function that combines your objective, your cost, with your constraint, right? So this is the thing that you're trying to minimize. And what's in the parentheses here is your constraint. And the way it's formulated, why did I write it as D transpose W minus 1? Because it's just by convention, we say that whatever the constraint is, let's say the constraint is C, we have to say that the constraint C is equal to 0. We make sure that it's a function whose value is 0. And so saying that D transpose W is equal to 1 is the same as saying D transpose W minus 1 is equal to 0. So that's why it's written like that. And now we have this new variable that's appeared, which is called lambda. And lambda is called the Lagrange multiplier. And the way to think about this is that lambda, you should think about lambda as informing where we place that green point, essentially. So what Lagrange came up with is that we need to solve two sets of equations simultaneously. So we need to do the same as before, except that we need to take the gradient of L and set it to 0. So that's basically what we were doing before. And we need to take the derivative of the Lagrangian with respect to the Lagrange multiplier lambda and also set it to 0. And this is really quite clever if you think about it. It took me a long time to wrap my head around this.
They're equal.
Right, because what is this? What is the derivative of L with respect to lambda? In this function or in any function? Exactly, it's just a constraint, right? So, and what are you saying? So if this is just a constraint, you're saying just a constraint is equal to 0, which is exactly why I formulated like this. Because by solving this, you're ensuring that the W that comes from here is going to satisfy the constraint, right? So I mean, this is really brilliant, because this now, what this does is it converts a constraint problem into an unconstrained one. And now you can use the same tools that we used in the previous two slides to solve a constraint problem. And so I don't have it on the slide, but I do actually want to solve this problem with you guys on the board, because it's, I think if you see it, if you actually see it worked out, you will you'll understand it more. And then we'll use fmincon, which is the function that does this in MATLAB. Okay, so I have it solved on paper just in case I have a senior moment on the board, but okay. What do I want to do? Stop share? I wasn't even sharing. Okay, that's not good. Okay. So if I go back to the Zoom now, will I see the board? Okay. How to do this? So I'm not going to assign numbers to A or D. I'm just going to solve it generically for any. So this is the thing that I want to solve. So I want to find W that minimizes my quadratic subject to this constraint. And so the first thing I do is I'm going to write my Lagrangian, which is equal to W transpose AW plus lambda E. And so the first thing I need to do is take the derivative, take the gradient rather of the Lagrangian with respect to W, which is here equal to what? 2AW plus what? What's the, anyone help me with the gradient of this term? Exactly. That's lambda D. And that's it. And then there's the.
So we're not worried about that.
Yeah, it's a good question. So no, because if it was, the answer is no in this case. If it's just a vector, product. So if you, the way to think about this is if you have something like, let's actually do it with the D. So the way this would work is you have. So this is already, so D is a column vector. When it's transposed, it's a row vector. And then, so this is what it looks like. So if you multiply this out, this becomes D1 W1 plus D2 W2, and then so the derivative with respect to W1 is D1, and the derivative with respect to W2 is D2, and then that is exactly, so if this is a column vector, that's exactly equal to D. But there are if you have matrices, then you have to worry about the transpose. But there's no matrices here. And then derivative of the Lagrangian with respect to the Lagrange multiplier is just our constraint. All right. So so I have it's kind of like two equations, two unknowns, except that they're not scalar equations. They're vector equations. So so I need to set these to 0 and solve. So what the question? So I want to use substitution here, right? That's like the most fundamental technique for solving. Is the camera on the board? I know. So I want to solve these with substitution. So my question is, how do I proceed here? How do I proceed? What's the first thing that I should do?
You solve for D or W.
Yeah, and so yeah,
And then plug it in.
plug it in. So which equation should I use? The first or the second, do you think?
First one is D is equal to
Yeah, the first one is. Why?
D is equal to 1 over W.
This one is hard, right? This one is actually impossible, I think. Because if I do D transpose W is equal to 1, right? There's no solution for that. Exactly, yeah. But in the first one, yeah, exactly. Exactly. So I'm going to use this guy. I'm going to use number 1. And I'm going to say 2AW is equal to minus lambda D. And then exactly like you just said, I'm having a really hard time with the D's. If you guys ever have kids, there's something called occupational therapy now for kids. And I could have really used occupational therapy. Did not exist in 1980s communist Poland. And so but you know, the communist in me, I'm not really communist, not at all actually, but the guy who was raised in communist Poland in me is like, is this stuff low-key? It's like occupational therapy. I think it's legit. Like the people that do it seem like I think it's evidence-based mostly, but it's like right on the border between like, you know, on one end you have like palm reading or bloodletting, and on the other end you have like modern medicine, like occupational therapy, somewhere in between there. And I don't know exactly how close to each end it is, but anyhow.
I have a bunch of friends who'd be very insulted by that.
Really, I'm sorry. I mean, I hope it's evident.
I would say
we put our
more
daughter
that-
into it.
Yeah, I would say more that maybe like you're writing these and you're doing okay. So it's maybe the argument of how necessary is it, not is it like.
Oh, I see. Yeah, I agree with
Like,
that.
Like PTs and OTs like spend a lot of time studying physiology. And
Oh,
so-
PT, yeah,
But like OT
No,
also
P-
is just fine.
yeah. right. Well, that's a good way of putting it. Yeah.
It depends, because OTs for kids are like rating, but OTs for someone who gets injured is different. You gotta teach them to use their hand again.
Right.
Yeah.
Ah,
Yeah, somebody, my sister does that, so.
You want you over?
She would, yeah.
yeah.
But she didn't want to.
I gotta cut that out.
Keep paying bills.
That's fine.
Well said. Yeah, I was speaking from the context of OT for kids, but yeah.
Or this
Yeah.
the context of bowling.
Yeah. Yeah, no, I could have really used it. I could have, because yeah, fine motor skills. And it just makes your life it makes your life harder if you don't have good fine motor skills. That's the truth. Anyhow, I digest. This is our solution for W here, right, from this equation. And now what do I do with this?
The road can be a.
The other one, thank you. Yes.
impossible.
It is. Now it's possible. It's totally possible. Now it's possible. So now what I'm going to do is put this into 2. And so I have I'm gonna have to try, I'm gonna leave it. I have this basically, and so the transpose, so do you guys know if I have, let's say matrices A, B, and I a product, and you guys know what the transpose of a product is? No. It's B2, A2. So you, and so here, what's gonna happen is, well, the scalars just come out. Scalars are just scalars, and then I have dt, and because A is symmetric, its inverse is symmetric, and so the transpose of A inverse is just
Shouldn't there be another?
this is I screwed this up. Sorry.
You should have a transpose D and a D.
It's I did it. I plugged it into the wrong. So I don't even have to transpose it. Oh, I know how to transpose it.
That equals 1, right?
Plus one.
-1 is yeah equals yeah. That's right. No. It's it's because this should be this, right? There's no. Oh no, it's right.
It's just equals 1.
Yeah, let's write it as that. So I have the transpose A. And so now I can, what this allows me to do is allows me to solve for lambda, basically. So I'm going to call this lambda star is equal to -2 D transpose. So now I have so now I have my optimal lambda, which is huge because now I can go back and plug this lambda into here because this is I don't know what the value of the lambda here needs to be to make this W star. But now I can plug it in. And when I plug it in, get something that looks, math is like this thing they say about math. When if it looks good, it doesn't necessarily mean it's right. But if it looks ugly, it's wrong. And this is going to be it's just going to be equal to. But this is one of these cases where it just looks right. This is my solution for W in the rectangle there, right? So it's inverse of A multiplied by D divided by D transpose A inverse D.
You can't cancel the is not right.
No, you
It's not
can't.
right with division.
It's not, it's a good question, but keep in mind that this is a vector, this is a scalar, right? So this is, I wrote it like this, and this is often how it's written, but this is really, this really should be written like this.
In MATLAB, it wouldn't accept the dot there.
No, MATLAB will accept this.
No, whenever you divide vectors, it's always like you have to plug a dot first. Otherwise, it doesn't tell you why you're wrong. It just complains.
No. I mean, yeah, wait till you, like if you think MATLAB is, the thing with MATLAB is, MATLAB's philosophy is we'll let you try it, we'll let you try anything, and it may break. Other programming languages, they will not even let you try it, like C or C#, like we won't even let you compile it, like you won't even get to run it. It will just say, no, this syntax is unacceptable. You did not define this variable beforehand. All right, so All right. Yes. Where are you?
You wanna share screen?
I do, but I also want my MATLAB to reveal itself. All right. I was waiting for that. Somebody was gonna say it. I've been watching a lot of YouTube videos about like web programming, and actually I'm surprised at how many developers actually use Windows. I don't know. All right. So let's define, where is it? The constraint, right? So this was our, I'm gonna run it to here. All right. What's that?
You didn't even dot divided. You were right. It's right.
Because it's a scalar. That's
Yeah.
why you don't need it. It's, if you want to divide, okay, so let me show you.
You did dot multiply. That's
Yeah, but like if you have random 1,5, right? And y is just a number. I can do x divided by y. Oh, oops. But if you have x is equal to random 1,5 and y is equal to random 1,5, then we'll not, oh, this will probably give me a matrix now. They've changed it. Oh no, it does. What is that? A vector. See, but it used to give you an error. You used to have to do this. But now
It's not the same thing.
What is this?
it's the pseudo, and I believe it's like this least squares inverse. So this is if you have two vectors. So what this was doing is find what number multiplies one vector to get it as close as possible to the other vector. All right. So we're gonna do this constrained minimization. So the first thing we're gonna do is we're gonna define our objective function, and we're gonna define our constraint here. I need to get this out of the way. Good step. That step, yeah. All right. So now I need to use function fmincon. So what is it's constraint optimization, and how do I see the help so I can show you guys? Doesn't give me. Right. So this is, it's very flexible. It gives you a lot of features. So A and B, we didn't do equality. So you can do inequality constraints. So like, well, like you see here, you can find x's that are on the right side of a line, or you can find x's like what we're doing that exactly are on the line. That's what so we're going to be using options AEQ and BEQ here. And it gives you other, you can actually constrain your x to be within like a, I guess, I think these are called box constraints. So like x is constrained to be within a box. But we're not going to use any of that. We're just going to use the function, the starting point, AEQ and BEQ here. So let's define that. Right, so our function is defined here, is just our quadratic. This is our start, this is our initial guess of the optimal value. I have no inequality, so I leave A empty and I leave B empty. And this is AEQ, so you have to transpose it because it has to be, it's just the document. If you look back at the documentation, they want each constraint to be on a row. And so D is a column, but obviously D transpose is a row. And so this means that 0.7 times W1 plus 1.6 times W2 is equal to 1, basically. This is these two inputs here. That's our equality constraint. All right, so let's go ahead and see. Let's run this. It says local minimum found that satisfies the constraints. It says objective function is non-decreasing in feasible direction. So this here means that it was only searching along that line. All right, and now let's see what the W star is. Negative 0.0488, 0.634. And now let's evaluate moment of truth. Let's see what our Lagrange multiplier says. And it says the same thing. Right, so good, that's great. And I think I have 4 minutes. So what I'm gonna try to do is it would be really cool if we could plot this. So let me see if I can figure this out. I'm going to use something called mesh grid. I'm going to try to draw these contours. Because what I'm wondering is, what is the relationship between, so that optimal point, I think there's a geometric property between where that optimal point lies and the contours. And I believe that it's tangent. I believe it's tangent to the contours. And I want to try to show that here. So to plot a function in 2 dimensions, we need to define our grid, which is W1 and W2. And then I'm going to try, the only tricky thing is how to do this matrix multiplication here. What's that equation? No, it's not up on there anymore.
Wait, W was a vector. No?
You can't, if you want, it's a two, it is, a small w is a vector. The point is, I have to evaluate this function. I think it's like this, hold on. Let me see if this works. Oh, I'm gonna call this F2. Now I can use one of MATLAB's contour. I have no idea it's gonna work. No, I wish I had that equation up on the board now. So, okay, hold on. It was. Yes, thank you. Thank you. That's awesome. No, that's all good. Thing is, I think that's what I oh no. I had it right. I had it right. It's just that I had to, hopefully this works. Thank you. Will this evaluate? No. All right. Anyways, that's too bad. Basically what I need to do is This will come to me literally the minute I get back to my office. But what I was trying to do was draw the contours, and I was going to put down the point where the minimum is. And actually, you know what I could do here? I do what's this is oh, it's saying that I have a all right, I give up. I will start next class with